In the previous video, we were introduced to Newton's Toolbox equations, a set of relationships between the fundamental kinematics quantities that apply when acceleration is constant. In this video, we will apply them as a demonstration of how to solve physics puzzles. This course is about more than physics. It's about developing a way of analyzing physics puzzles. In this class, every physics puzzle is solved in the same basic process. And that means this process will be one of the most important things you see in this series. Let's apply the process to this puzzle. A car is at rest on an open road. It accelerates at a constant rate of 3 meters per second squared until it reaches 39 meters per second. How long did the acceleration take? The first step in solving any physics puzzle is to draw a picture. This is needed for 3 reasons. First, it forces you to visualize the situation described in the puzzle. Physics puzzles are not math problems. They correspond to something that occurs in real life. The picture is proof that you understand what is taking place in the puzzle. Second, it is a psychological aid. If you are stuck on a puzzle, you can always revisit the picture to ground yourself. Third, I will take off points if there is no picture. Step 2 is to clearly show the endpoints of the motion. Remember how a few videos ago we examined the motion of an object by taking 2 photos of it at 2 different times? The endpoints clearly label on your picture where the object is when the first photo was taken and where it is when the second photo was taken. Here, we've superimposed the 2 photos so there's less to draw. Step 3 is to clearly set the origin and axes for the situation. This establishes where we are starting all the measurements from and which direction is positive. Now, the motion of the car doesn't depend on how you set your axes, so you could set your axes whichever way you want as long as you stay consistent. The right way to set the axes is whichever way makes the problem easiest to solve. Often, that means placing the origin at one of the endpoints and pointing the positive axis in the direction of motion, but there are exceptions. Here, I've placed the origin at the back bumper of the car when the car was in its initial position, and I've set rightwards as the positive direction. On the puzzles I give on the homework, doing these first 3 steps correctly will grant you 1/4 of the points for the puzzle. Step 4 is to list the unknowns. Remember, there are 5 kinematics variables. We have to return to the question and see what was being asked to identify which of these is the unknown. How long did the acceleration take? That's asking for a time. So time is the unknown here. Step 5 is to list the known quantities. Remember, each kinematics equation contains 4 of the kinematics variables, so you will need to be given the values of 3 of the kinematics variables in the question. It accelerates at a constant rate of 3 meters per second squared. That's an acceleration. Until it reaches 39 meters per second. That's how fast it's traveling when the second photo was taken. That is its final velocity. We need a third known value. Look at the first sentence. A car is at rest. That is another way of saying the initial velocity is 0. So now we have 3 knowns. Step 6. Find the equation that relates the knowns to the unknown. The unknown is time, while the knowns are acceleration, initial velocity, and final velocity. Out of the Toolbox equations, there's only one that uses these 4 specific variables. That's equation 1. So that's the one we have to use. Step 7, the last step. Substitute the knowns and solve for the unknowns. the acceleration is 3 meters per second squared, initial velocity is 0, and final velocity is 39. Simplify and isolate time. We get time equals 13 seconds. So that's the solution. It takes 13 seconds for the car to increase speed from 0 to 39 meters per second if the acceleration is 3 meters per second squared. Equivalently, you could say that 13 seconds elapsed between when the first and the second photos were taken. Now, suppose I provide the same situation, but I ask a slightly different puzzle. Instead of asking how long the acceleration took, I ask how far did the car travel until it reached its top speed, starting from rest. For this new puzzle, the drawing, endpoints, and axes are the same as before, but in step 4, where we ask what the unknown is, that's where things change. How far did the car travel? That's asking for a displacement, not a time like what we did earlier. In step 5, the knowns are the same as before. But in step 6, things once again change, because we need a different equation, one that weaves together displacement, initial velocity, final velocity, and acceleration. Equation 4 is the only one that will do that. Step 7. Substitute for the knowns and solve for the unknowns. The acceleration is still 3 meters per second squared, initial velocity is still 0, and final velocity is still 39 meters per second. 39 squared is 1,521. 0 squared is, of course, 0. And all that equals 2 times 3 times displacement. Simplifying and dividing both sides by 6, we get a displacement of 253.5 I hat meters. That's the displacement that the car experienced between the two photos. We have now solved 2 kinematics puzzles. I should perhaps point out that 39 meters per second is 88 miles an hour, and the car we've been following is indeed a DeLorean. The Toolbox equations are very well suited for free fall, objects falling under gravity with zero or negligible air resistance. Near the surface of a planet, acceleration due to gravity is very close to constant and always points towards the center of the planet. On Earth, acceleration due to gravity has a value of 9.81 meters per second squared for any object towards the center of the planet. Of course, the value is different on other celestial bodies. Here is a coconut tree. A coconut, initially at rest, falls from the tree. It takes 3 seconds to hit the ground. How tall is the tree? We can solve this using our process. Step 1. Draw a picture. Here's a coconut tree. Step 2. Set the endpoints. The puzzle starts the instant the coconut starts falling from the tree. The puzzle ends just before the coconut hits the ground, maybe a nanosecond before. These are the points where we are taking our 2 photos. Step 3. Set origin and axes. For a bit of diversity, I will set the origin at the second photo near the ground, and I will set positive to point upwards. I know this isn't the easiest way to set the axes. I'm just using this approach to show that you would get the correct answer either way. Step 4. List the unknowns. The question asked, how tall is the tree? That's talking about displacement. Step 5. List the knowns. The coconut is initially at rest. That means V initial equals 0. It takes 3 seconds to fall. Finally, it's in free fall near the surface of the Earth. That means its acceleration is 9.81 meters per second squared towards the center of the Earth. Again, that's the negative direction, the way we've set our axes. so the acceleration is negative. Step 6. Which equation weaves together the unknown delta x with time, acceleration, and initial velocity? Equation 2. That's what we must use. Step 7. We now plug in all the information we have and solve. V initial equals 0, acceleration equals negative 9.81, and time equals 3. 0 times 3 is 0, so that term cancels. Half of negative 9.81 is negative 4.905, multiplied by 3 squared. Solving, we get negative 44.145 meters. So the coconut was displaced. In other words, the coconut tree must therefore be 44.145 meters tall. If I could offer a word of advice, if you ever decide to visit my native country of India, don't walk directly under any coconut trees. How about this one? You throw a rock upwards off a 25-meter cliff. It lands 3 seconds later with a speed of 23 meters per second. What was the velocity with which you threw it? Step 1. Draw a picture. Remember, you threw the rock upward, so it reached its peak and then descended until it landed. Step 2. Set the endpoints. We'll take the first photo a nanosecond after the rock leaves your hand, and the second photo a nanosecond before it hits the ground. Step 3. Origin and axes. To keep things simple, I will set the original height of the rock, just as you threw it, as the origin. We will set downwards as positive. Step 4. List the unknowns. What was the velocity with which you threw it? That means the velocity in photo 1, the initial velocity. Step 5. List the knowns. The displacement is 25 meters, positive since we set downwards as positive. The final velocity is 23 meters per second, again positive. The time is 3 seconds. Step 6. Find an equation that weaves the unknown initial velocity to the known displacement, final velocity, and time. That's Toolbox equation 3. Step 7. Solve. Substitute the known information. We get 25 over 3 equals Vi plus 23 all over 2. 25 divided by 3 is 8.33. Multiplying both sides by 2, we get 16.67 equals Vi plus 23. Finally, subtract 23 from both sides. The initial velocity is negative 6.33 meters per second. Negative because we said upwards is negative. In other words, you threw the rock with a velocity of negative 6.33 meters per second. This video showed the standard procedure for solving all physics problems. On homeworks, each problem will be out of 1 point. 1/4 for the picture, endpoints, and axes. 1/2 for the choice of the correct equation and correct analysis. And 1/4 for the right answer. In the next video, we will see more challenging applications of the kinematics equations.